Download this code from codegive.com, link in the description below. OK, let's dive deep into VLSI timing constraints, particularly focusing on setup and hold times. Lecture 7e likely builds upon previous concepts like basic logic gates, sequential circuits, flip-flops, and clocking strategies. We'll cover the core principles, practical implications, and illustrate them with verilog code examples. VLSI timing constraints, setup and hold times. In synchronous digital circuits, timing constraints are critical for reliable operation. They dictate how the timing of the clock signal and data signals relate to ensure the sequential elements, primarily flip-flops/registers, capture the correct data. Violating these constraints leads to metastability, unpredictable behavior, and potentially system failure. The two primary timing constraints we'll discuss are setup time and hold time. 1. Setup time, T sub su/sub or T sub setup/sub. Definition The setup time is the minimum amount of time that the data signal must be stable before the active clock edge, rising or falling, depending on the flip-flop's design, for the data to be reliably captured by the flip-flop. Intuition Imagine trying to take a photo of a moving object. You need to aim the camera and focus before you press the shutter. Similarly, the data needs to settle to its correct value before the clock edge arrives, giving the flip-flop's internal circuitry enough time to recognize and store the data correctly. Violation If the data changes too close to the active clock edge, i.e., if the setup time requirement is not met, the flip-flop may enter a metastable state. Metastability means the output of the flip-flop doesn't immediately resolve to a clean logic 0 or logic 1. It might hover at an intermediate voltage level for an indeterminate amount of time before eventually settling. This can cause unpredictable behavior in downstream logic. Mathematical representation Arrival time of data at flip-flop input plus setup time equals arrival time of clock edge at flip-flop clock input. Or T sub data underscore arrival slash sub plus T sub su slash sub equals T sub clock underscore arrival slash sub. Visual representation 2. Hold time, T sub h slash sub or T sub hold slash sub. Definition The hold time is the minimum amount of time that the data signal must remain stable after the active clock edge to guarantee reliable data capture. Intuition After you press the camera's shutter, you need to keep the camera still for a brief moment to avoid blurring the photo. Similarly, the data signal needs to remain stable for a short period after the clock edge arrives, ensuring the flip-flop correctly latches the data. Violation If the data changes too soon after the active clock edge, i.e., if the hold time requirement is not met, the flip-flop might incorrectly latch the old data, or again, it might enter a metastable state. Mathematical representation Arrival time of data at flip-flop input plus hold time equals arrival time of clock edge at flip-flop clock input. Or T sub data underscore arrival slash sub plus T sub h slash sub equals T sub clock underscore arrival slash sub. Visual representation 3. Clock to output delay, T sub co slash sub or T sub clkq slash sub. Definition The clock to output delay is the time it takes for the flip-flop's output to become valid after the active clock edge. This is a key parameter that influences the speed of your circuit. Intuition After the photo is taken, there's a small delay before the image actually appears. Similarly, after the clock edge captures the data, there's a delay before the flip-flop's output, Q, reflects the new data. Visual representation 4. Metastability ****. Definition ***Metastability is a state where a flip-flop's output is neither a clean 0 nor a clean 1, but somewhere in between, and its value is unpredictable for a period of time. This usually happens when setup or hold time constraints are violated. Impact metastability can propagate through downstream logic, causing errors and system malfunction. Dealing with metastability often requires special techniques like synchronizers, more on that later. 5. Why are these constraints important? Reliable operation meeting timing constraints ensures that sequential elements capture data reliably, leading to predictable and correct operation of the digital system. Performance understanding and optimizing timing constraints is essential for maximizing the clock frequency of your circuit. Design closure timing analysis and correction, timing closure, are critical steps in the VLSI design flow. If you don't meet timing, your circuit won't work. 6. Factors affecting timing constraints Technology node smaller technology nodes, example 7 nanometers, 5 nanometers, generally have faster transistors, leading to smaller setup times, hold times, and clock-to-output delays. However, interconnect delays become more significant at smaller nodes. Temperature higher temperatures generally slow down transistors, increasing delays. Voltage lower supply voltages generally slow down transistors, increasing delays. Process variations manufacturing variations can cause differences in transistor characteristics, leading to variations in delays. Layout the physical layout of the circuit has a major impact on interconnect delays. Logic gate types different logic gates, example NAND, NOR, XOR, have different propagation delays. Load capacitance the load capacitance at the output of a gate affects its delay. Larger loads increase delay. 7. Verilog code example Let's illustrate with a simple example of a D flip-flop and how setup and hold times play a role. We'll first create a D flip-flop module, and then we'll demonstrate a hypothetical scenario. Now, let's create a test bench to demonstrate setup and hold time considerations. This example is simulated timing, not actual physical timing, so it's conceptual. We'd use static timing analysis tools in a real design flow. Explanation of the test bench *. 1 clock generation always 5 CLK equals CLK, creates a clock signal with a period of 10 ns, frequency of 100 MHz. 2 Initialization RST_n is initially set to 0, active low reset, to reset the flip-flop. After 10 ns, it's released, RST_n equals 1. 3 Setup time violation test *. D equals 1, sets the data to 1. 4, waits 4 ns. This means the data changes 4 ns before the clock edge. The comment // hypothetically, let's say T2 equals 1 ns, indicates a hypothetical setup time requirement of 1 ns for the flip-flop. Since the data changes only 4 ns before the clock edge, and the setup time requirement is 1 ns, this is a setup violation. The flip-flop might not capture the data correctly. 4 Hold time violation test D equals 0, changes the data to 0. 1, waits 1 ns. This means the data changes 1 ns after the clock edge. The comment // hypothetically, let's say th equals 1 ns, indicates a hypothetical hold time requirement of 1 ns. Asterisk since the data changes 1 ns after the clock edge, this is a hold violation. 5 setup and hold time met, correct. Asterisk d equals 1, changes the data to 1. Asterisk 6, wait 6 ns. This means the data changes 6 ns before the clock edge. Asterisk data is valid for long enough for the flip-flop to capture correctly. How to simulate and analyze, important note. Asterisk simulation tool asterisk you would simulate this verilog code using a simulator like Model Sim, Questa Sim, Icarus Verilog, or a similar tool. Asterisk SDF, standard delay format to realistically simulate setup and hold time violations, you would typically use an SDF, standard delay format, file. The SDF file contains timing information, setup times, hold times, clock to output delays, that are specific to your target technology library. You would back annotate the SDF file into the simulator so that it understands the actual timing characteristics of the flip-flop. Asterisk static timing analysis, STA in real-world VLSI design, you don't rely on simulation alone to verify timing. You use static timing analysis, STA, tools, example PrimeTime, Tempus. STA analyzes the circuit paths and verifies that all timing constraints are met without running simulations. STA tools are essential for design closure. Asterisk viewing simulation results asterisk in the simulator, you would observe the output queue to see how it behaves during the setup and hold time violations. Ideally, the output would show metastability or an incorrect value being captured. However, this behavior is heavily dependent on the simulator and the accuracy of your timing model. Simple simulators might not accurately model metastability. 8. Addressing timing violations, mitigation techniques. Asterisk buffer insertion asterisk inserting buffers along the data path can delay the data signal, allowing more time to meet setup constraints. Asterisk clock skew engineering asterisk intentionally skewing the clock signals to different parts of the circuit can help balance timing paths. However, clock skew management is complex. Asterisk redimming asterisk moving registers around in the circuit to rebalance the path delays. This is usually done automatically by EDA tools. Asterisk gate sizing asterisk changing the sizes of transistors in logic gates to increase or decrease their driving strength and delay. Asterisk floor planning and placement optimization asterisk improving the physical layout to reduce interconnect delays. Asterisk slower clock frequency asterisk sometimes, the simplest solution is to reduce the clock frequency to give the circuit more time to operate correctly. This is a trade-off, as it reduces overall performance. Asterisk two-phase clocking asterisk in some cases, using a two-phase clocking scheme can provide more flexibility in timing. Asterisk asynchronous FIFOs for clock domain crossing, CDC when transferring data between clock domains, regions with different clock frequencies or phases, you must use special techniques to avoid metastability. Asynchronous FIFOs, first in, first out buffers, are often used with synchronizers. 9. Metastability mitigation in clock domain crossing, CDC. Metastability is a serious concern when signals cross between clock domains. Here's why, and how to mitigate it. Asterisk the problem asterisk when a signal transitions between two clock domains, the sampling flip-flop in the receiving domain might violate setup/hold times because the arrival time of the data is asynchronous to the receiving clock. This can lead to metastability. Asterisk the solution, synchronizers asterisk a synchronizer is a circuit designed to reduce the probability of metastability. The most common type is a two-stage or multi-stage flip-flop synchronizer. Explanation asterisk. Asterisk data underscore in is the asynchronous input signal from the sending clock domain. *CLK is the clock signal in the receiving clock domain. Stage 1 and Stage 2 are two flip-flops connected in series. How it works. 1. The first flip-flop, Stage 1, is the most likely to go metastable. 2. The second flip-flop, Stage 2, gives the output of the first flip-flop more time to settle to a stable value, 0 or 1, before it is sampled. 3. The probability of both flip-flops being metastable simultaneously is greatly reduced. Important considerations for CDC***. Multi-bit signals. Synchronizing multi-bit signals is much more complex. Gray coding is often used to ensure that only one bit changes at a time, minimizing the risk of glitches during synchronization. Handshaking protocols. For reliable data transfer, handshake protocols are often used in conjunction with synchronizers. Thorough verification. Clock domain crossing circuits require careful verification to ensure they operate correctly under all conditions. 10. Advanced timing concepts, beyond Lecture 7a, but related. Slack is the difference between the required time and the actual arrival time of a signal. Positive slack means the timing constraint is met, negative slack means it is violated. STA tools report slack values. Clock jitter. Clock jitter is the variation in the clock period from cycle to cycle. It can affect timing margins and increase the risk of timing violations. Clock skew. Clock skew is the difference in arrival times of the clock signal at different flip-flops. While clock skew can be detrimental, controlled clock skew can sometimes be used to improve timing. False paths. False paths are paths in the circuit that are never activated during normal operation. Timing analysis tools can be instructed to ignore these paths. Multi-cycle paths. Multi-cycle paths are paths where data takes multiple clock cycles to propagate from one flip-flop to another. Key takeaways. Setup and hold times are fundamental timing constraints in synchronous digital circuits. Violations can lead to metastability and unreliable operation. Understanding these constraints is essential for designing high-performance and reliable VLSI systems. Use static timing analysis, STA, tools and SDF files for accurate timing verification. Be aware of clock domain crossing, CDC, issues and use proper synchronization techniques. This detailed tutorial should give you a solid foundation in VLSI timing constraints. Remember to practice with simulations and examples, and consult your textbook and course materials for further information. Good luck.